Hey everybody, I hope you're doing well. Today we're going to continue to talk about aromaticity. So what we did last time was we looked at benzene and we were starting to get an understanding, hopefully, of how these pi bonds can move around and essentially create a benzene structure that looks like this. All right, we then talked about some of the gateways for aromaticity, like it needs to be cyclic, it needs to be planar, it needs to be consisted of, it needs to have a bunch of pi bonds in conjugation, or lone pairs of electrons. And this is being very stubborn right now. No, I didn't want that. Sorry, guys. The tech gremlins are here today. So we got pi bonds in conjugation, negative charges, pairs of electrons, and positive charges. Then we got to this one that was a little rough. You need an odd number of electron pairs for aromaticity, or an even number for anti. Excuse me. Aromaticity. Finally, oh no, there is no finally, sorry. Weird morning. All right, so here we are. And then we looked at how benzene passed the test. It's got to be cyclic. If it's not cyclic, it's not going to be aromatic. You have to assume planarity, and all the pi bonds, anions, lone pairs of electrons, and cations have to be in conjugation with each other. So let's look at, I think we did this one last time, but we're going to do it again. This is the cyclopentadienyl anion. This has a net negative charge. So let's see what the options are here. Is it cyclic? Yes. Is it planar? Assume so. Is everything in conjugation? Yes. How many electron pairs does it have? It has 3 electron pairs. How did I come up with that number? 1 from the pi bond, 1 from the other pi bond, and 1 from the anion. Now to counterpoint, so this is, sorry, got excited, aromatic. Now, to counterpoint to this is the cyclopentadienyl cation. Now, it's going to fill all the same niches that it did up until now, except for 4. It has an even number of electron pairs. 2 from the cation, 2 from the pi bonds, and the cation brings nothing to the party. So this is anti-aromatic. This is bad news, folks. Aromaticity is a tremendous stabilizing force. Anti-aromaticity is a tremendous destabilizing force. Let's look at a couple others. And this one's hard to draw. 7-membered rings are really hard to draw, but that's what we're going to try to do here. 1, 2, 3, 4, 5, 6, 7. Hey, yay, I did it. Now, this is formerly named the tryptophan cation. You know as much about it now as I do. All right, let's take a stab at this. Is it cyclic? Yes. Is it planar? Assume so if I'm giving it to you. Is it, what else can we say about it? Is everything in conjugation? Absolutely. How many electron pairs does it have? I count 3. 2 from, oh, excuse me, not 2, 1. 1 from each pi bond. Okay, now I'm going to show you a couple of weird ones. This is pyrrole. And believe it or not, it is aromatic. And the reason it is aromatic is that pair of electrons is part of the aromaticity. So we get odd number of electron pairs. The same principle applies in this one with a sulfur, thiophene, and this one with an oxygen, furan. Now, both thiophene and furan have 2 pairs of electrons. So you might look at this and go, eek, anti-aromatic. And your estimation would not be wrong, but I'd like to point something out. In both of these, only 1 electron pair is involved with aromaticity. The other electron pair just sort of hangs out in front of it. So if we were to draw, let's do furan here. There's furan. Pi bonds here and there. One of the electron, you know what, that is a terrible drawing. Let's just do it again, but bigger. There's no reason I have to use that little space. Here are the p orbitals. Looking, there's the steeple. When it comes to making it aromatic, that pair of electrons is involved in the aromaticity. Whereas, pardon me for just a moment, so I can get to the color I want. There we go. And down here, whereas this pair of electrons, not involved in aromaticity. Okay? Now, let's look at something else. What we're going to look now is electron donating and electron withdrawing. And we're going to analyze this through a big-ass aromatic ring. All right? So now here we are. If something is electron donating, what that means is it pushes electrons through the conjugation. So let's take a look at our example here. This is really starting to piss me off. All right, there we go. Let's look at our example here. All right? So we shove electron density in. The thing about electron donating groups is they always have a lone pair. So we can add the electrons into that carbon, and which is going to break the carbon-carbon pi bond we've got here. So I'm going to redraw this. Oh, sorry, here. I'll let you write it down. Now I'm going to redraw this over here so we have a little more room to play with. Oh, yikes, it's already 10 minutes. How the time flies when we're having fun. I gotta ask, are you guys as exhausted and tired of 2020 as I am? Because, damn. So there's our first resonance structure as it's added electron density in. Here's the second. And here's the third. Do you need a negative charge or do you need a pair of electrons? The answer is whichever you would actually prefer. You know me, I don't get stuck on a lot. There you go. Now, if we do the resonance hybrid for this, so solid lines wherever there is sigma, whether there are sigma bonds, dashed lines where there are pi bonds being either made or broken, and finally this with the partial negative charges on those three carbons. Ladies and gentlemen, I want you to study this structure really well because it's going to become very important moving forward. Now, I'm at almost 13 minutes. This thing gives me the bum's rush at 15, so I want to leave you with this problem to work on. That's what happens if there was an electron donating group. I want you to think about what happens if there is an electron withdrawing group. And the answer to that is going to be, I'll do the first step for you. There you go. I want you to draw out the rest of the resonance structures here, and then I would also like you to draw the resonance hybrid for me. And we'll discuss this when we come back for the next video. Everybody have a great day. Stay healthy, stay safe, stay hydrated.